Alright, so what we have done so far is that we have shown, we have got the geometric intuition. We've also had a proof which told us that at most n steps is required. Now, there is again one very powerful theorem in linear algebra which helps to formalize this. The proof is a slightly longer proof. I'm going to do half the proof to give you the flavor of it. The remaining half, if you are interested, you can read it in the book, okay? Because it will take a long time to drive it. But let me state the theorem. It's a very powerful theorem and it's used in all the analysis of this conjugate gradient method, okay? It has a very cool name also. It's called the expanding subspace theorem. And what is, before we get into the grungy details, what is the, why am I telling you this? This is a way to formalize all the intuition that we have had about the method so far. Okay, so if you have a more theoretical bent of mind, you will appreciate formalizing it, formalizing all the hand waving intuition that we have had so far. Okay, so I'm just going to state the result to begin with so that we can appreciate it. Okay, say using the CDM. So when I say using the CDM, immediately what does it imply? There were two requirements for CDM. Which were they? Asymmetric positive definite, fine. After that there were two requirements, which were give me a set of conjugate directions and then do exact line search along each one of those directions, those alphas. That is what makes a CDM. Okay, so that gave me a sequence xk, okay, starting from some arbitrary x0, okay. We were minimizing phi, my objective function phi, okay. So the first, there are two consequences of the expanding subspace theorem. Okay, the first is Rk transpose Pi is equal to 0 for I belonging to 0 to k-1. Let's just note it down and then we'll give some intuition to it. Okay, in an affine space, okay, so these are the two consequences of the theorem. Consequences in the sense that the relation between these two statements is actually a if and only if condition. Okay, so let's just, it looks a little tedious, let's just interpret this in words. So what is the first thing saying? Remember, keep in mind what we are doing is we are formalizing the intuition that we have had. So intuitively we should immediately be able to appreciate what's going on. So the first statement is saying the residual at the kth step, that is Rk, is orthogonal to what? To all the previous conjugate directions. We kind of expected that to happen, right? Because every time we are going along one direction, we are never revisiting it. So whatever is the balance in that direction is perpendicular to the new directions it goes into, right? So you can see how this is a formalization of that intuitive idea. That is step 1. Is that clear what is being said? Residual at the kth step is orthogonal to all previous directions in which I have walked. That means I never revisit a direction. Right. Second, we all know what a vector subspace is, right? I take a bunch of vectors and I say the span of that forms a vector subspace because their linear combination stays within that vector subspace. That is a vector subspace. To a vector subspace, if I add a constant term, it no longer remains a vector subspace because the origin is excluded, right? When I say span of vectors means linear combination of those vectors. If I set the coefficients of linear combination to be 0, what do I get? the origin. So the origin always belongs to a vector subspace. The moment I add x naught and without any alpha 0 behind it, that means the origin is not guaranteed to lie inside. So this makes it, instead of a vector subspace, it makes it a affine subspace. Fancy way of saying something very simple. So in this affine space, so what is this affine space? Take the k conjugate direction so far. I am at step k, take the previous, take the k direction so far. Out of that, create some affine space. Okay, fine. Constraining x to live only in this smaller space, try to minimize the objective function. It is saying that the xk, the kth iterate, so xk is not any xk, it is the kth iterate of my conjugate direction method, is actually the minimizer of phi. I am interested in a global minimizer of phi. That means x1 to xn, all n coordinates I want the best thing, right? So if I were looking at the total solution, I would say linear combination of p0 to pn minus 1. That's where my solution lives, because I have n linearly independent vectors. The solution has to be a linear combination of the basis function, right? That's what I want. But this is saying something a little bit different. What is it saying? If I restrict myself to a k dimensional subspace. Why k dimensional? Because it is being described by k basis vectors, not n. Now when I am restricting myself to k basis vectors, what is this result saying? That even though you are remaining constrained to a k dimensional subspace, the solution that you get, xk, is the best in terms of minimizing my objective function. If I want to minimize any more, I have to expand the subspace. That's why this name comes expanding subspace. So at every step, I am doing the best possible. So in the first, so let's take it very simple. In the first step, where am I? X naught plus span of p naught. What is that? X naught plus alpha times p naught. That is an affine space. What am I doing? Finding the best alpha. I have a closed form expression for it. I get the value of alpha naught. Can I do any better for phi? I can't do any better. This is the minimizer along, why I am constrained to go along only p naught. Fine, I got it, right? So step 0, that's why. When I add now, go to step 2. I have a now p1 also. What is the best I could do? So like this I keep adding. So I am growing the subspace in which my solution lives. Till finally, in at most n steps, I reach the final solution. Okay. So getting this intuitive understanding is far more important than following the nitty-gritty details, right? You will forget, even I forget the details of the proof after some time. But if you keep this in mind, how do you interpret this, right? 5 minutes ago when you saw this, it just looked like mathematical symbols, but now it has come alive a little bit more. You know what is going on over here. So that's the key thing to keep in mind. And in general, this is a skill all of you should develop, that when you read a theorem, first step is to get intimidated by it. Second step is to take literally every symbol and convert it into plain English. You see a transpose, orthogonal. You see RK, you say residual. You say P, you say conjugate direction. Residuals are orthogonal to conjugate direction. So that begins to make a kind of a geometric picture in your mind. Okay. Any questions about interpretation here? Okay, I'm going to give you half the proof so as to, just to give you a flavor of it. Okay, we already know one thing, that this residual is Ax minus b. Okay, so just to remind you, which is also grad phi. Okay. I'm going to define a function h, which is a function of sigmas, which is something like this, phi of x0 plus, now I am going to take only the k dimensional subspace of it. So my summation is going to be j is equal to 0 to k minus 1, okay, sigma j pj. Okay. So how many sigmas do I have? The sigma over here is a vector, right? I have k sigmas. So what is this function telling me? This is the function that I get by restricting my x to be in a k dimensional space or an affine space, okay, right. Is this function, is it convex? How did I define phi? Half x transpose ax minus b. So, is this also affine? I mean, is this also convex? Obviously, this is also convex. If it is a convex function, does it have a minimizer? Has a minimizer, we have seen that, right. So, therefore, so answer is yes, and it has in fact the minimizer, is it unique? For a convex function, is the minimizer is also unique, as a okay. Right. So, if it has a unique minimizer, that means the rate of change of this function with respect to each of the sigmas, what can we say? So, what I am asking, close, I can write, so we can expand this by chain rule. But what do we expect the answer to be at the optimal? 0. If this function has a minimizer, it will be expressed as some values of the sigma. So, the rate of change of this therefore is going to be 0 for all I belonging to 0 to k minus 1, right. Because why? It is the best, because it is the because these sigmas minimizer. Right. And here is where the chain rule comes in. Immediately I can write this partial derivative. How do I write it? Grad of this whole thing, x naught plus summation sigma j p j transpose multiplied by what? If I just apply, right, pi is equal to 0, right. This is just use of chain rule. I didn't do anything special over here. I did chain rule over here, and we are almost home. Why? Because now when I look at the expression for the residual, the grad phi is also the residual. So, this implies that this is the residual now at, right, or let me put it like this, xk, right, transpose pi equal to 0 for all I belonging to 0 to k. Right. Notice I am constraining xk to be only in the affine space, it is not in the entire space, it is only in this affine space, and I am showing you that the residual is orthogonal to all the previous conjugate directions. Okay. So, I mean, it is not surprising, I expected this to happen, there is nothing very complicated over here. Okay. So, actually what have we proved over here? We have said, we have assumed 2 to be true and we have proven 1. That is what we did, right. We assumed that I pick a x from this affine space, okay, which is the minimizer of phi k. If it is the minimizer of phi k, what follows? dh by d sigma equal to 0. Chain rule gives me this, which leads to residual at the kth step is orthogonal to all previous search directions. So, I got my given 2, assuming 2, I got 1. Okay. I can, as you can imagine, I can also repeat the process where I start from 1 and go to 2, okay, but we won't do it here. It's not very difficult. If you see the proof in the textbook, they do it by induction. It's a nice refresher on induction. Okay, so this is what, this is all the background that I wanted to give you until we start in the next class with the conjugate gradient method. Okay. So any doubts in what we've done so far? You notice there's nothing very complicated. Where basically this is like a applied linear algebra. We're using properties of conjugacy and our calculus over here. Okay. Yeah, so we'll do the conjugate gradient method, and then as soon as we have done the basic version of conjugate gradient method, we're going to have a race between steepest descent and conjugate gradient method, and we'll see how the two of them perform head to head.